For this fifth lesson in fluid mechanics and medicine, I'll be discussing Pascal's law. The learning objective is to be aware of a number of non-intuitive, real-world phenomena that are the consequence of the pan-directional transmission of applied pressure through a fluid. There are a number of variations in how Pascal's law is formulated and worded, though they all describe the same general principle. Pressure, applied anywhere to an enclosed body of fluid, is transmitted within that fluid equally in all directions. This is an extension from lesson number 3 on hydrostatic pressure. Explaining it further will be much easier with a few examples. First, imagine we have a wooden barrel full of water. A vertical tube is inserted into the lid. If the maximum pressure the barrel can hold is 100,000 pascals, how high must the column of water be in order for the barrel to rupture? We know that the primary equation of hydrostatics is the pressure gradient is equal to the density of the fluid times acceleration due to gravity times h. In this case, when we talk about the maximum pressure the barrel can hold, it actually refers to the maximum pressure gradient. In other words, the pressure inside can be no more than 100,000 pascals greater than that outside, which is presumably atmospheric pressure. 100,000 pascals is not an atypical value for a wooden barrel. Let's then plug in the numbers. 100,000 pascals equals 1,000 kilograms per cubic meter times 9.8 meters per second squared. Solve for h and we find that it's 10.2 meters. That's right, if the total height of the barrel and the tube is more than 10.2 meters, the barrel will rupture. This may seem quite surprisingly low, even more so once you realize that our solution did not need to involve the diameter of the tube, and thus the diameter is irrelevant. So the tube, which can be 1 centimeter wide or smaller, and contain a total of less than a liter of water, can still generate enough pressure to rupture a barrel. It's quite counterintuitive, yet nevertheless true, and it's because of Pascal's law. The pressure created by the vertical tube, even if that tube is tiny in size, is still transmitted through the fluid equally in all directions, including out to the walls of the barrel. According to legend, this specific example was actually devised by Pascal, and he used his experience with it to formulate his law, though the story is probably not actually true. Let's look at another example. From lesson 3, we discussed a glass of water in which the pressure at the bottom could be calculated from the hydrostatics equation, where the pressure gradient is the difference between the pressure at the bottom and atmospheric, leaving this solution. What if, instead of the top of the glass being exposed to atmospheric pressure, we replace it with a piston that pushes down on the water with some force? In this case, the atmospheric pressure gets replaced with the pressure of the piston. If you recall, pressure equals force divided by surface area, so the piston pressure equals the force divided by the surface area of the piston, which, assuming it is a perfect circle, is equal to pi r squared, and we end up with an analogous solution. You may not immediately realize it, but this solution depends upon the fluid being non-compressible, which we said was an assumption made for liquids in elementary fluid mechanics, though this would not hold true for gases. If the glass below the piston was filled with a compressible gas, the density of the gas would be a function of the pressure applied to it, and our solution would look a bit more complicated. But let's apply this general concept of a piston imparting a force on a non-compressible liquid in a somewhat more complex situation. Imagine we have a system of 2 pistons of markedly different sizes, attached by a liquid-filled tube. There is some force pushing down on piston 1, which has a radius of 2 centimeters, and resting on piston 2, which has a radius of 10 centimeters, is a 500 kilogram weight. Inside the pistons and tube, instead of water, we'll have some type of oil. Given the radii of the 2 pistons, what is the minimum force that is needed to be applied to piston 1 in order for the weight on piston 2 to be held up against gravity? So the force of gravity due to the 500 kilogram weight must be equal in magnitude to the force imparted on piston 2 by pressure in the fluid. Since pressure equals force divided by area, we know that the pressure in piston 1 equals the force of piston 1 divided by the area of piston 1. The same relationship holds true for piston 2. The key principle to solving this problem is to recognize that the pressure in piston 1 must equal the pressure in piston 2, as a consequence of Pascal's law. Remember, a pressure applied anywhere to an enclosed body of fluid is transmitted within that fluid equally in all directions. So the pressure that the force from piston 1 imparts within the fluid inside piston 1 is transmitted through the connecting tube to the liquid in piston number 2. So we know that the force on piston 1 divided by the area of piston 1 equals force on piston 2 divided by the area of piston 2. And the force on piston 2 is equal to the force of gravity on the 500 kilogram weight, so we can substitute that in and solve for force piston 1. Force of gravity is mass times g, and our areas are pi r squared. And if we plug in the numbers, we get a total force of 196 newtons. That's the same force that a 20 kilogram weight has as a consequence of gravity. So the force that you would need to generate in order to lift a 20 kilogram weight, if directed onto piston 1, would be enough to hold up a 500 kilogram weight sitting on piston 2. As with the barrel example, this seems counterintuitive, yet it's true. This type of system of multiple pistons of varying sizes, connected by fluid-filled tubes, is known as hydraulics, which are used in an extremely diverse variety of machines that we encounter in everyday life, most notably the automobile. There's a number of ways in which Pascal's law is used in medicine, but one of the more obvious applications is during mechanical ventilation. Here we have a picture of the lungs, which receive air via a hollow conduit called the trachea, which branches into a right and left main bronchus, which travel to their respective lungs and divide and further subdivide into smaller and smaller airways until terminating in trillions of air-filled sacs called alveoli. In modern mechanical ventilation, which is undertaken when a patient is experiencing respiratory failure for any one of 100 reasons, a tube called an endotracheal tube is inserted into the trachea and air is delivered to the lungs under positive pressure. This means that the air moving from the ventilator through the endotracheal tube and into the lungs has a pressure that exceeds atmospheric pressure. The positive pressure that is present at the end of expiration phase of the respiratory cycle is simply called positive end expiratory pressure, or PEEP. As a consequence of Pascal's law, this PEEP, which is typically a value of around 5 centimeters of water, is applied within the endotracheal tube and is transmitted equally through the right and left main bronchi, is transmitted all through the successive diminishing airway branches until it reaches the peripheral alveoli, all undiminished. What benefit does PEEP have in treating respiratory disorders? Its complete role in pathophysiology is quite complicated, but on the most basic level, since PEEP is transmitted through the lung equally in all directions, the consequence is lung expansion. Lung expansion increases the surface area of the individual alveoli, across which oxygen diffuses into the pulmonary circulation. Thus, PEEP improves oxygenation within the bloodstream. In practice, for a number of complicated reasons, including intermittent obstruction of the small airways, PEEP may not be distributed perfectly uniformly, but for most ventilated patients, this is only a minor problem. That's it for Pascal's law. The next lesson will cover the continuity equation.